Alright gang, this video is going to be on confidence intervals, and first thing I want to do is I want to show you guys a little bit of what's behind the mechanics of confidence intervals. You can, or you may or may not share this with your students. I think it would depend on how well do you understand what I'm getting ready to try to present to you, and secondly, you have to be realistic and examine the level of students that you're working with. But first of all, think about confidence intervals. The two confidence intervals that we're going to teach to our students are a t-interval and a one proportion z-interval. All that means is if we have a z-interval, we're drawing from a normal distribution, mean 0, standard deviation 1. If we're drawing from a t-distribution, we have a distribution that's centered at 0, but the variability, the shape of the distribution depends on what we call the degrees of freedom. And degrees of freedom is really easy to calculate. It's just n minus 1. Now, let me give you an illustration. Again, you may or may not share this with your students, but let's think about the z distribution in what I would call a z interval. And let's say, for example, that sigma is known and mu is unknown. So we collect a sample and we get a sample mean and a sample standard deviation and a sample size. Well guys, in this case it's kind of strange because we have a population standard deviation and a sample standard deviation that are both known. This value will always trump this value in the cases where they're known. If we didn't know the population standard deviation, then we would be doing a t-interval. But let's just assume we've got some rare situation, rare occurrence here where the population standard deviation is known. Now, what's the central limit theorem tell us? Well, it first of all tells us that all the x bars will be normally distributed, centered at mu, which remember is unknown, and we'll have standard error sigma over the square root of n. So guys, this tells us that 68% of our sample means will fall between where and where. Between mu minus a standard error and mu plus a standard error. Let's focus on the middle 95%. So smack dab in the center of the distribution is mean, mu, unknown. And let's focus on this, the middle 95%. Well, what would this bound look like? Well, this would look like the mean minus 2 times the standard deviation. And this would look like the mean plus 2 times the standard deviation. But guys, we were being very relaxed when we created the 68, 95, 99.7% rule in using this 2. So let's go see what really in the standard normal distribution between what two z-scores gives us a better approximation of the middle 95% of our data. Well, I'm going to jump out of here and I'm going to go over to the calculator. And since I'm dealing with the normal distribution, I would go second distribution, go to number 3. Now my left value, the area below that, if you think about 95%, I'm missing 5%. So to the left of that 1 point would be 0.025. Mean 0. Standard deviation 1. Hit enter, hit paste, and you'll see that we have negative 0.196. Now, if I go second function entry, which will give me exactly what I put in before, if I look at the right-hand bound of that, then this is going to be 0.975. I've got the 95% in the center plus the additional 2.5% on the other end. So guys, here I get positive 0.196. So guys, going back to the drawing, instead of being between negative 2 and positive 2, negative 1.96 and positive 1.96 give me a lot better indication of the standardized scores for which 95% of the distribution falls between. So guys, going back to my original drawing, for all of the sample means, mu in the middle, this would be mu minus 1.96, standard deviation over the square root of n, and this would be the mean plus 1.96 times the standard deviation over the square root of n. That 6 there is going to drive me insane. So between these two values, 95% of our sample means. We've got a problem here. That's unknown. So let's come in and choose a mean at random. And let's just say we get this one right here. We don't know which one we got. We don't know where it is. But let's say we got that mean right there. Now, I want you to examine the distance from here to here. And I want to slide this over. So I want to slide this over and create a left mark for my interval. I want to slide this over the same amount and create the right bound. So this is the center of my interval, and then I allow myself what we call margin for error. Now, I want to ask you, is the value we're looking for contained in my interval? Well, the answer is yes. What if I'd received at random this sample mean? Well, let's think it through. That would have been from there to there, from there to there, also containing mu. Guys, at the end of the day, where is the only region of the distribution of sample means where I could build an interval around my sample mean and not contain mu? Well, it would have to be something out in the tails, and you got to think about the way the distribution is set up. There's only a 5% chance that I could get a mean up here or down here where the confidence interval wouldn't contain what I'm looking for. So, having said all that, let's work the first problem. Now, if I go back to the first problem, I'm going to need some things. So I'm going to have a lot going on here. Hopefully my computer doesn't lose its mind on me. So the first problem says the mean emission level for a new design of engine is unknown. Collected 10 measurements. We're going to use those to estimate with 95% confidence the mean emission level for all engines with this new design. All right. So the first thing to think about is we need to look at our data and calculate the descriptive statistics. So if we go to our calculator, and get rid of that stuff. Wow, the writing's really big, isn't it? So in case you're watching this video from Mars, I want you to be able to see it. Alright, so guys, you see that I have the measurements in L1. So now I want to go to Stat, go over to Calc, go to One Variable Stats, and I want to perform the descriptive statistics. On the data in the first column. That doesn't seem right. Huh. $13.9, $12.7. Huh. Okay, hold on, guys. I'm thinking that I have a typo. So 13.9, 12.7. Don't you love it when this happens? No, I guess not. So it looks good. So guys, let's get back to this. All right. So our mean is 17.17. Our standard deviation is 2.98. And my sample size is equal to 10. All right, cool. All right, so I've written this down. Now, the very first thing I want to do here, well, back up a little bit. Is realize that my population standard deviation is not given. Now, granted, your calculator is going to give you sigma x. You'll never, ever use that unless you're absolutely certain that all of the measurements you have make up the entire population. Clearly, we have 10 engines here. Clearly, there'll be more that will be produced. So the population standard deviation is not known. So the second thing I need, therefore, is my standard error. Will be equal to 2.98 over the square root of 10. And that's 0.9424. Next thing that's really important What's the underlying probability distribution look like? When the population standard deviation is not known, we deal with the t-distribution. T-distribution is a function of your degrees of freedom, which is n minus 1. So guys, we are making our calculations based on the t-distribution, degrees of freedom equal to 9. Okay. Now, what we need to know in this distribution between what two t criticals? Does 95% of our distribution fall between? Well, got some work to do. Need to go back to our calculator. Go second function, distribution. And come down to number 4. As number 4 is inverse t, it works just like inverse norm, except still one area below, so we have a 95%, so we have 0.025 to the left of the mark we're looking for. The degrees of freedom is equal to 9. And paste that, hit enter. So we have negative 2.26 is the left bound, and you should know by now that positive 2.26 is going to be the right bound. So negative 2.26, positive 2.26. So guys, in this distribution, (95% of the t values will fall between negative 2.26 and positive 2.26. But we know that the t value can be calculated from this expression. So we know that our x bar is 17.7, right? No, 17. Minus mu over 2.98 over the square root of 10. So gang, I have negative 2.26 So the first thing I want to do is I want to multiply through by 2.98 divided by the square root of 10. Hopefully you're following along with me here. So when I multiply through, I get negative 2.26. And whoa, why don't we do it right? 1, 3 to positive 2.13. Now the next thing I want to do is I want to subtract 17.17 from each side. My dog's losing his mind. And I get 15.04. Now, almost forgot my negative there. Guys, what I'd like to do now is multiply through by -1. So, greater than. Which we all know is more effectively written this way. So guys, our 95% confidence interval is going to be (15.04 to 19.3). Now guys, typically when you teach your students to construct confidence intervals, you're going to use the formula. And let's just go through the formula, make sure that we understand all the names of all the parts. Guys, your X bar is called your point estimate. Your T star is called your T critical in this problem. That's the plus or minus 2.26. And Sx divided by the square root of n is called your standard error. Your T critical times your standard error is called your margin of error. So let's go back to our handout. So estimate with 95% confidence the mean emission level. So what we ended up with is 15.04 to 19.3. Now, what I always like to do is just double check with the calculator, and let me show you how to do that. So if we go to our calculator, keep in mind that we have our data in L1. We can come down to number 8, which is our T interval. And guys, we have our data, so let's go over and select that. We have our data in L1. We want a 95% confidence level. And we can calculate and get our answer. So 15.04 to 19.3 is what we came up with, which is exactly what the calculator gave us. Now, the easiest way to find the margin of error is to take the biggest number minus the smallest number divided by 2. So if I take 19.3 minus 15.04 divided by 2, I get the margin of error, which is 2.13. So guys, your margin of error for your problem That was right there, right? 2.13. Yeah. All right, cool. All right, gang. The next problem deals with percentage of homes with internet service or high-speed internet service. So let's go take a look at the that's not right. I thought the yeah, that's what we want right there. That's interesting. Okay, I want to add a couple of problems here. Just kind of get the ball rolling. All right, so let's work this. So what percentage of households has high-speed internet service? Random sample. So we have 58 out of 150. All right, we want 90%. So let's keep that in mind. So guys, here's what we know. P is unknown. P hat from our sample. I want to go ahead and convert that to a decimal because it's going to be easier to deal with. So guys, 38.7% of our sample has high-speed internet. Now, remember guys, there's a difference between your sample and population. This is one of infinitely many samples that we could have collected. This is one of infinitely many decimal representations of a sample. So what we need to do things correctly is we need to take the information from our sample, add margin for error, subtract margin for error, and create a 95% confidence interval. Keeping in mind that this phenomena is modeled by the Z distribution. So guys, in the Z distribution, what's smack dab in the center? P, the unknown, what we're looking for. Between what two Z values does 90% of the distribution fall? Well, to find this one, we need inverse norm. 0.05, 0.01. And for this one, we need 0.95, 0.1. So guys, if we put that in our calculator, inverse norm, 0.05, 0.1, we give negative 1.645. And over here we get 1.645. So we know that from negative 1.645 between positive 1.645, that 90% of our z-scores fall. Well guys, the z-score formula for this problem is equal to this. So the first thing I've got to do is put in my calculator and find what is the square root of, I forget what was p hat, 0.387 times 0.613 over 150. And when I get that, I get 0.0398. So guys, let's clean this up a little bit. 1.6 or negative 1.645 less than p hat minus p over 0.0398. Guys, clearly I need to multiply everything through by 0.0398. So I got negative 0.0654. And 0.0. Alright gang, let's add 0.387 to both sides. Or I'm sorry, subtract 0.387. So I get negative 0.452. And I will get 0.0654 minus 0.387 on the other side. Hopefully I don't make any typos. Negative 0.322. Multiply through by negative 1. Put it in convenient form. And appreciate the fact that this is better written like this. So gang, our confidence interval is 32.2% to 45.2%. So we can estimate with 90% likelihood, 90% probability, 90% confidence that the percentage, that this interval, 32.2% to 45.2%, contains the percentage of households who has high-speed internet service. All right, guys, let's test it out. Let's go to our calculator. Now let's go to stat. Let's go over to test. And we got to come down quite a bit here, and as slow as my computer is moving, this is probably going to take a month or so. And what we're looking for is at A, which is a 1 prop Z interval. Now the commands here are really easy. I think we had 58 out of 150. And we have a confidence level of 90%. Come down to calculate. And we get just as we would think, well, okay. That was fun. I need some music or something. This is... Alright, so gang, we get 32.2% to 45.2%. Now, so going to part B, I ask you to find the margin of error. And the margin of error is always going to be easiest to find by taking the biggest number minus the smallest number in our confidence interval divided by 2. And your students are going to ask you, well, why does that work? And that's something you should easily be able to figure out. So our margin of error will be plus or minus 6.5%. All right, boys and girls, let's go to the handout. So what's our 95% confidence interval? So this indicates there is a 0.90 probability. This interval contains P, which is the with internet service. Guys, the margin of error was plus or minus 6.5%. Alright guys, the next problem, what sample size would reduce the margin of error to 2%? Now let me go back over to the come on buddy, don't let up on me now. Alright, let's go back over to this, and the confidence interval formula for a proportion is p hat plus or minus z star times the square root of p hat times 1 minus p hat over n. This is the point estimate, this is the z critical, this is the standard error, and this is the margin of error. So ultimately, guys, we need this expression to turn out to be equal to 2%. Well, first and foremost, you should know that you never use the percentage in calculations. So we change that to 0.02. Z critical was 1.645. Now students will ask you all the time, should we include the plus and the minus? Well, technically, we're looking for a plus minus 2%. And technically, this C critical here is plus or minus. Guys, that notation just complicates things. So let's do the calculations without. P hat was, I don't know why I can't remember this. I think it was 0.387. So guys, we need to be able to solve for n, and this is something that should be pretty easy for. Well, it should be very easy for you guys. So I end up getting 1604.88. So guys, n would always be rounded up. So our sample size would be 1605. So holding everything else constant, the rate of our p hat sample size would be 16.05. Well, guys, that's it. That's the end of the confidence interval training video. So that's all I got.